So in my previous lectures, I gave some introduction to Donaldson-Thomas invariants and BPS invariants on Calavera seaford. So today I give the local version of it and also its categorization of these invariants. So far, the categorization is not yet available in the case of compact Calavera seaford. But in the case of quivers with potential, the quiver with potential is regarded as some kind of local version of Calavera seaford. And in this case, we have a very defined definition, and we can study its properties. So first, let me go about quivers with potential. So again, now let's say Q is quiver. So this is Q is vertices and edges, and we have the two maps which associate each edge to the source and target of each edges. So this is now quiver. And then we can associate some associative algebra called path algebra. So this is given by some compositions of edges. And the product is naturally defined by connecting the edges. So this is the path algebra. And the superpotential this is an element of this quotient space. So this is called potential. So because I'm taking the quotient of this vector space, so each potential is represented by element of this form, like AI1 to AK, EI1 to EIK, where so this is now a form of cycle of the cycle, like this. So then the pair of this Q and the quiver and also potential W. So this is called quiver with potential. So the given potential of the quiver, it defines some function on the modular stack of representation of the original quiver Q. So this is given by taking traces of each cycle. So more precisely, let's take dimension vector. So the dimension vector is given by this element. And we can, as usually, consider the modular stack of representation of Q. That is, let's say, RD. So this is given by direct sum. Very obvious. Whereas let's say this is D is like DI. And each VI is, so this is the I-dimensional vector space. So there is a action of GD. Which acts here by conjugation. And as usual, we take the quotient of this finite dimensional vector space by this algebraic group. It forms the quotient stack. So this quotient stack is modular stack of representation of this quiver Q. But given this potential, we can define the function on this stack. This is given by the trace of this potential W. That is, given this element, we can apply each matrices to this cycle and then take trace of the composition of the matrices. It gives the GD invariant function on this space of representations. So it gives a well-defined function on the modular stack of Q representations. So we are interested in the critical locus of this function. Critical locus. So this is a closed substack of this. This is a smooth stack, and this is possibly singular stack. And in fact, this is regarded as this is the modular stack of Q W representations. That is, so this is modular stack of Q representations satisfying revisions. So this is satisfying revisions given by the derivation of this potential for each h in Q becomes 0. So this is a very important stack, and in fact, this gives the local model on the modular stack of the semi-stable shapes on Calabian seafold. So, so this is so the average of this one is also mentioned in my lecture in my previous lecture. That so let's say x is Calabian seafold. And let's consider modular stack of semi-stable shapes with fixed chunk character and also with fixed polarization, which gives stability condition. It admits good modular space. So then locally on the good modular space, so this modular stack is modeled by this critical locus for some quiver with potential. So locally on S, so this modular stack is isomorphic to some critical locus of some function, critical locus of some quiver with potential.
So this is only analytic?
Yeah, analytic, yes. So maybe analytic locally. We also have to be careful about the potential in this setting because, so in this case, W is the element of this path algebra. So this means this is a finite sum. But now, so this W is not necessarily finite sum. This is element of the formal compression of this potential, but which has some convergence values. So now this W is like the convergent potential. So this is formal sum, formal infinite sum of this kind of thing, but there is some bound of the coefficient. So in this way, it is very important. In particular, if we want to prove some property of the modular stack of semi-stable sheaves, for example, like the computation of the BPS sheaf. So the BPS sheaf is like the push forward of the vanishing cycle complex to here and then take the first Parabolic cohomology. So locally, on here, it can be also described in terms of some quiver with potential. And moreover, so in my previous lectures, I say some genericity conditions which make the BPS invariant to be integer. And yes, let's say so this is like H semi-stable for some polarization H. And under some genericity condition, this quiver Q can be taken to be, sorry, for some quiver with potential, and this quiver Q can be taken to be symmetric quiver. So symmetric quiver means that if you consider the number of edges from I to j for two defined vertices, then the number of the edges in the opposite direction is also same. So in fact, Davis-Meyhard proved the integrality of the BPS invariant in the setting of symmetric quiver with potential. And we can combine the result with this local structure of the modular stack of semi-stable sheaves on Calabi-Yau threefold to show the integrality of the BPS invariant in the geometric setting. Yes. H is, yes, so this is, so H is some polarization, like ample divisor. So this is which I mentioned in my first talk, so that given ample divisor, it gives notion of stability conditions. So for example, let's consider this example. Let's take Q to be the one vertex with three loops, let's say x, y, z. And then take the potential given by zxy minus yx. So then let's consider the d-dimensional representation of this quiver with this potential. So let's say V is like d-dimensional vector space. So then this stack of representation of this quiver Q, so this is endmost the direct sum of this end V. It's 3 times with quotient by JV. And we have the trace function. So this is given by sending x, y, z to the trace of this one. If you take the critical locus, then it gives the modular stack of such representations with relation given by this derivation of the potential. But if you calculate the derivation of this potential, for example, the derivation by z gives the commutator relations. And this is also same for the derivation of the other variables. So the critical locus of this function so this is the same as the modular stack of such representation satisfying this commutator relations. In other words, giving such a point is equivalent to the representations of the commutative polynomial, the commutative polynomial ring with 3 variables. So this is nothing but the modular stack of the zero-dimensional sheaves. Zero-dimensional means that the support is zero-dimensional on C3 with whose length equals to d. And of course, so this is non-compact Calabi-Yau threefold. And so this picture gives the local model of the moduli stack of semi-stable sheaves with zero-dimensional support. So then, as I said, so this gives the local model of the moduli stack of semi-stable sheaves. So we want to consider the category of multi-factorizations of this smooth stack with function given by trace of the superpotential. So this is which I can say it's like a local model of the categorical DT theory. But so this is interesting. This is interesting when stable and semi-stable are not the same. And in fact, when stable and semi-stable are the same, then this is almost isomorphic. So this is GM job, and the associated quiver is only just one vertex with a dimension vector 1. So this is not interesting. So this is interesting when the semi-stable and stable are not the same. And so in the case of the stable and semi-stable are not same, we should consider BPS invariant. And in this case, we should also consider the categorification of the BPS invariant. So that is now I'm going to introduce. So this is which I'm going to say about so-called quasi-BPS categories. So this is defined to be certain subcategory of this category of multi-factorizations. So let me first give some notation. So first, let's say TD. So this is maximal torus. And also let's take M beta. So this is the character lattice. And also let's take WD. So this is Y group of GD. So the if you consider the Y fixed locus, so this is regarded as the moduli. This is regarded as the set of line bundles of the classifying stack of TD, and this Y invariant part is regarded as the so this is regarded as the line bundle over the classifying space of GD. So in particular, given this element, we can interpret it as a line bundle over this modular stack of representations. So then first, define such a categorification of BPS invariant. In the case, there is no potential function. So then, by definition, let's take delta in. So this depends on choice of this peak of BGD. So this is also element of the Y invariant part of this character lattice tensored by R. So given this delta, we define the Sorry, yeah. From here, I assume that Q is symmetric. Then I define MD delta to be the subcategory in the derived category of coherent sheaves on XG. So this is defined to be generated by object of this form, gamma GD chi tensor O. So this is some irreducible representation of GD, and chi is the element of this character lattice, and so this is the irreducible representation whose highest weight equals to chi. So chi is the element of this MD, and such that so it's chi plus rho. So rho is this is so-called half sum of positive root. This is contained in half sum of 0 beta plus delta. So this is so-called Minkowski sum. Of TD weight of this representation space, RD. So, so this is some point of inside. The right-hand side is some point of inside MD. So chi is element of MD. So this inclusion holds in the space of the character lattice tensored by R. So I just give example about this choice of this weight chi. Beta, yes. So beta is so this is one of the TD weight of RD. Yes, it's yeah. So I just give instead of giving more detail about this definition, I just give examples. So let's consider the quiver Q given by one vertex and also with some loops. And let's assume that the number of loops is the auto number, let's say 2m plus 1. And yes, and let's consider the d-dimensional representation of this quiver Q. So then the maximal torus. So this is the maximal torus of GMV. So this is d-dimensional torus. And this character lattice. So this is the rank D Arbian group of finite rank. So I can express it as like this. So each beta 1 to beta D are the standard representations, standard weight, the weight of the standard representation of GLV. So then this condition is that, yes. So first, rho is written by like half of equals some j, beta I minus beta j. And this Minkowski sum is, so this is in this case, so this is given by like this. J. So this is because so these are the weights of the endomorphism space V plus 2m plus 1. So this bound is coming from the fact that this is direct sum by 2m plus 1 copies. And the weight of TD weight of end V is given by in this way, beta I minus beta j. So this condition means that the chi is given by like this, chi I beta I, and it should be given by like this, ij beta I minus beta j, where aij satisfies that this is minus m minus 1 j to m. So this is just writing down this condition. And also, this chi must be some highest weight of some irreducible representation, so that it must be a dominant weight. So if I write that down in this way, then we also have that, this kind of inequality. Anyway, this is now purely combinatorial question. What kind of weight appear in this definition? And the most simplest case is the m equals 0, where there is only one loop. And in this case, this combinatorics is of course very easy. Say, for example, when m equals 0, this means that there is only one loop. And also, for simplicity, let's ignore the contribution of this choice of delta. Then one can check that this condition is possible only if chi equals 0. It is possible. So this is just the elementary check. So this means that this category is just generated by the structure sheaf of this modular stack. So in that case, MD0, so this is generated by, let's say, so this is, let's say this KD is the endomorphism algebra of V, where this is d-dimensional. So this is, so this is now the modular stack of representation of this Jordan quiver, and this is generated by this structure sheaf. This one. dB cof of KD over GD. But now, so this quotient stack admits a good modular space. And in fact, there is a natural map, KD over GD to GD. So geometrically, so this is regarded as moduli stack of zero-dimensional shapes on A1. And this is like sending the support of the zero-dimensional shapes on A1. So, but the possible support consists of some point in A1. So this is to be just a symmetric product of A1. And of course, this is also isomorphic to AD. Anyway, so we have the pullback map from here to here. And the image, this is now smooth. So this is also the same as the derived category of coherent sheaf on this good moduli space. So in fact, so this is very similar to the definition given by, well, also this is motivated by the construction of so-called non-commutative Quepanto resolution of the singular GRT quotient given by Spenko and Vandenberg. So-called non-commutative resolution of the what is singular scheme. That is, so they consider the direct sum of these vector boundaries and then take its endomorphism algebra. So then it gives some non-commutative resolutions. And in some cases, it gives also non-commutative Quepanto resolutions. And this kind of subcategory is also used in Hyperleister and Sun. So they use this kind of category to construct some equivalence between two derived categories with different stability conditions connected by some birational transformations, so which they call as magic windows. But so in both cases, so they consider such subcategory when there is some stability condition where stable and semi-stables are same. But in our case, we want to consider the case where stable and semi-stable are not the same. For example, in this case, there is no stability condition where stable and semi-stable are the same when d is bigger than or equal to 2. So nevertheless, so this subcategory is important to consider, and in that case, this gives some categorization of the BPS invariant. So then this is the definition of the subcategory when there is no potential. And in the case there is a potential function, we can also define in the similar way, just imposing the potential function. So now again, so this is Q and V, so this is symmetric quiver with potential. So then we define the subcategory of the category of multifactorization on XD given by like so this is our notation that this is multifactorizations whose factors are given in this category. So this means that so this is subcategory of object such that each pi lives in this one. Another way to say is that so this is the subcategory of multifactorizations. So this is the subcategory of XD plus W So this is subcategory of the category of multifactorization over this smooth stack, such that each term of the factorizations are given by generated by the if-distributed representations of this form, satisfying the weight condition which I described before. So one of the subtlety about this definition of the category is that in the case there is no potential function. So this is rather easier to understand because at least this is generated by these representations, and we can just try to compute the home space of these representations in order to understand this category. In particular, so if the corresponding chi is we have the corresponding highest weight, then this category is non-empty. But if there is a potential function, so even if there is such a object MD, it's not clear whether we have the corresponding object in the multifactorization because we need to find some also maps, alpha and beta, satisfying these relations. So in practice, it is much more difficult and harder to study this category rather than this category. Yes?
What is X cleared up?
This one?
No, sorry, when you say alpha composed with beta is equal to something.
Trace W. Yes.
And what is like before trace W? X?
Before so yeah, so P0 and P1 are the coherent shifts on XD. And alpha and beta are the morphisms of this category. And the condition is that the composition of these maps are given by multiplication by this function, trace W. Yes? Yes, so the symmetric condition is I'm using because I consider this weight point up. Yes, I'm using this symmetric condition because yes, so in this definition of this MTW, so I need the symmetric condition of this weight point up. So this weight point up, I want this weight point up to be somehow symmetric.
So the trace will be symmetric?
Trace is, what do you mean symmetric? In trace is symmetric. So yeah, I think so there's nothing to do about the symmetricity of this trace function. This is only to do with the point op. So then, yes, so this is one more theorem. So this is my paper with Toda. So this indicates that there is a relationship between this category and the BPS invariant of this quiver with potential. So for each quiver with potential, so there is some delta such that if we consider dimension of the topological case theory of this subcategory, it equals to the dimension. So this is dimension of the BPS cohomology. But for precise, you have to take the so-called monodromy invariant part, so of the vanishing cycle. So because that, so the BPS sheaf is, so this is the applying the vanishing cycle functor to the intersection complex. So this was like phi to SW of the intersection complex of the good moduli space. So I recall that, so this is good moduli space. This is smooth stack, but this is singular stack. And we have the trace function which factors through the good moduli space because of the property of the good moduli space. So then I'm applying the vanishing cycle functor of the intersection complex, and that was the in some way somehow a definition of the BPS sheaf on here. But so this is given by these vanishing cycle functors, and the vanishing cycle functor admits some monodromies. And this invariant means that, so this is the invariant part of the monodromy action.
So the right-hand side is the total sum.
Yes, total sum, yes, yes. Depend on the, yeah, for this is the same for I equal 0 and I equal 1. Yeah, so yes. Yeah, that's in that case there's no monodromy. Monodromy action is trivial, yes. So now I'm going to explain how to decompose the original category of multifactorization in terms of this quiver, in terms of this category SD. So, but anyway, so in this, from this theorem, I would say it is like the, this is called quasi-BPS category. You want to ask it? Yeah, maybe. So, yeah, maybe I think that we can try to write the periodic cycle homology to. You're asking about whether there's some categorical invariant which recovers the also non. Yeah, yeah. So at least the case of it that does not work. So maybe I think we So right, periodic cycle homology may give the answer for that. Yes. I'm going to talk about how to decompose the category in terms of this one. So I'm going to into the categorical version of the whole product, categorical whole product. So this is also defined in a similar way to the usual whole product. Let's say decompose D dimension vector to the let's decompose the dimension vector. So this is di into zi. And let's consider x d1 to dk. So this is a moduli stack of Q iterations of Q representations. One. Such that the dimension vector of Ri quotient by -1 is equal to di. So then we have the two maps. So by associating this iteration to the associated group, we get a map from the product of So this is okay. So this is sending R dot to the associated graded. And also we have that map XD. So this is associating each filtration to the last piece of this one. Again, so this is now the proper map, so we can do the pull back and push forward. So this pull back, push forward also makes sense in the categorical level. And yes, we also have the potential function. So here we have the potential function from this smooth stack. And here we take the sum of the potential function on each product factors. Now I give it a commutative diagram. So, so then because of this commutative diagram, we can also pull back the category of multifactorization from here to here, and then push forward category of multifactorization from here to here. So this gives the functor. W to here. So this is called the categorical whole product. So then using this categorical whole product, we can decompose this category in terms of these quasi-BPS categories. Again, so this is BP. But at this moment, so we impose some technical assumption, which is not much essential, but in order to make the statement easier, let's assume that the number of edges from two different vertices, so this is even, and also number of loops, so this is odd. For example, this works when the one vertex quiver with the number of loops are odd numbers. So then we have the semi-orthogonal decomposition of this form. Ti, which satisfying this condition. Okay. And so this functor is given by the categorical whole product, also with composition with some tensor line bundle. So I have to explain about this notation. So this is like SD of delta, where delta is given by like so this is V, sum of like beta I. So these are the weights of the standard representations of GD, and now V is integer, and this D, so this is defined with just the sum of the factors of the dimension vector. So this is regarded as some categorical version of the so-called PBW theorem by Davis and Meinhardt. By Davison and Meinhardt. So they give the decomposition of the vanishing cycle cohomology of the symmetric quiver with potential in terms of some symmetric product of the BPS cohomology. So it is given by, it is regarded as some kind of categorical analog or categorical approximation of such a statement. So finally, I mentioned about the categorical version of the Mach-Mahon function on the for the modular stack of zero-dimensional subschemes on C3. So in the case, so the yes, I talk about categorical Mach-Mahon formula. In my first lecture, I said that the generating series of point counting DT invariants on Calabian seaford is expressed in terms of the Mach-Mahon function. So this Mach-Mahon function is some series whose coefficient is the number of the plane partitions. We also have some similar formula in the categorical setting, which is given by the some sort of semi-orthogonal decompositions. So the relevant quiver which we consider is like Q plus equal this one, say x, y, z. And consider the dimension vector C to CD. So let's note that this is not a symmetric quiver. But we don't consider the quasi-BPS category for this quiver, but we consider quasi-BPS category for this quiver. And then express the categorical Donaldson-Thomas theory for the Hilbert scheme of points C3 in terms of quasi-BPS category over here. In that case, the modular stack of Q plus representation with this dimension vector 1D, this is the same as V plus V quotient by GLV. And also let's take the potential as before. So this is z of xy minus yx. We have also the trace function. One. So then we have the GIT semi-stable locus. So this is the same as that. As I said, so the modular stack representation of this potential is, so this is the modular stack of representation of the of structure C of C3. But if you don't put the potential, so this is just the framing of that representation. So this semi-stable locus consists of that. Now Q is the representation of this part, and this arrow gives the framing, and this framing gives the surjection from this non-commutative free algebra to here. Another way to say that this is like the non-commutative Hilbert scheme of point of C3. So then if you take the critical locus of this function to here on this n Hilb, so this is the same as the usual Hilbert scheme of point. So in this way, if we consider the multifactorization of n heap of C3D with this superpotential trace W, so this is regarded as categorical Donaldson-Thomas for the heaped scheme of point on C3D. So this is some modular space of stable shifts on this non-compact Calabi seafold. And this is explicitly given by some critical locus over this smooth locus. So this is now smooth quasi-projective variety. And this is regarded as some categorization of the DT invariant associated with this modular space. But the DT invariant associated with this one is given by the McMahon functions. So we have this them. So we can write down this categorical DT for heaped scheme of points of C3 in terms of this quasi-BPS category. This is given by D1 plus dk, and also we have this. So this is regarded as categorical McMahon formula, and conjecture, which is almost proven, but the so this is work in progress with Sabine Curtis and ourselves, so that this category might be equivalent to this category of multifactorizations of this symmetric, of this quotient stack with zero potential. In particular, so this should imply that the K theory of this one, the dimension of the K group of this one is the number of the partitions of D. At the level of K theory, we proved it. So, for example, by decategorifying this to the K theory, we can recover the McMahon formula. So, in that sense, so this is regarded as categorical analog of the McMahon function, and this is also relative to the Mackay correspondence for heaped scheme of points on C3. So in the next lecture, based on this description of quivers with potential, I will describe the case, more global case, like the modular stack of Higgs bundles and so on, and discuss with the relation of the Dolbeault Langlands conjecture. So I stop here. Thank you very much.